Welcome to today's Explainer. I am incredibly excited to guide you through this, because today we are strapping in to explore one of the most awe-inspiring achievements of human engineering, the sheer power and the really elegant physics behind rocket propulsion. Space exploration, as we know it, it simply would not be possible without these incredible systems. We're going to look at exactly how they generate the immense force required to accelerate a spacecraft, overcome gravity, and perfectly place vehicles into orbit. It's this fantastic blend of raw chemical power and precise physics. But before we get into the nuts and bolts, just think about how we move here on Earth. If you're swimming, your arms push against the water, right? If you're walking, your feet push against the ground. Even an airplane's propellers are pushing against the air. But out in the absolute vacuum of space, there's zero air. There's literally no matter. So how on earth do you move when there is absolutely nothing to push against? It's kind of the ultimate paradox of space travel, and solving it is exactly what makes rocket science so fascinating. Here's our flight plan for today's explainer. First, the vacuum of space. Second, the physics of thrust. Third, inside the rocket engine. And finally, powering the final frontier. Let's get right to it. Section 1. The vacuum of space. Overcoming the ultimate roadblock. Okay, let's dive into this fundamental difference. To overcome Earth's relentless gravity and push through all that aerodynamic drag during launch, a spacecraft obviously needs a massive amount of energy, but it also has to bring its own air. Think about standard jet engines. They just pull oxygen directly from the surrounding atmosphere to burn their fuel. Rockets totally don't have that luxury. To operate during atmospheric ascent, out in the vacuum of space, and during deep space maneuvers, a spacecraft actually has to carry both its fuel and its oxidizer on board. This self-contained setup is what makes rockets the only practical way to launch payloads beyond Earth's atmosphere. They literally bring their own atmosphere with them. Moving on to Section 2, the physics of thrust, the laws of motion and momentum. So you likely recognize Newton's third law of motion, right? For every action, there is an equal and opposite reaction. It's kind of like that classic skateboard and bowling ball analogy. Imagine you're standing on a skateboard and you throw a really heavy bowling ball forward as hard as you can. What happens? You instantly roll backward. Well, in a rocket, that bowling ball is actually high-temperature, high-pressure exhaust gas. By violently expelling those gases out the back, the rocket gets pushed forward. You aren't pushing against the vacuum of space, you're pushing against the mass of your own exhaust gas. Inside the vehicle, this builds into a really active 5-step sequence. Step 1, the fuel and oxidizer mix together. Step 2, combustion ignites them, producing intensely hot, high-pressure gases. Step 3, those gases violently expand through the nozzle. Step 4, the exhaust leaves that nozzle at a terrifyingly high velocity. We're talking thousands of miles per hour here. And finally, Step 5, that equal and opposite reaction force, the thrust, propels the rocket forward. So the rocket gains momentum going forward, while the exhaust carries momentum in the exact opposite direction. It is just an incredibly elegant balancing act of physics. Section 3. Inside the rocket engine, anatomy of a propulsion system. Now, a typical rocket engine isn't just one big chaotic explosion. Actually, scratch that. It's a highly controlled sequence that requires a few major components to work perfectly. It starts with the propellant tanks, which safely store the fuel and oxidizer. For liquid rockets, these are kept entirely separate. Then the feed system kicks in, using these incredibly complex turbopumps. And get this, some of these pumps are so powerful they could drain a typical backyard swimming pool in a matter of seconds. The system meticulously delivers the propellants from the tanks directly into the heart of the engine at massive flow rates. And what's absolutely mind-blowing about this next part is the sheer, terrifying extremity of the environment. The combustion chamber is the true heart of the rocket engine. This is exactly where the fuel and oxidizer from the feed system finally meet and react chemically. Because they release such enormously large quantities of thermal energy and high-pressure gases, this specific chamber has to be engineered to withstand temperatures that would, without a doubt, effortlessly melt solid steel. I mean, it is literally containing a continuous, perfectly controlled explosion. But, you can't just let that explosion expand in all directions. You have to harness it. And that is achieved by the frankly brilliant design of the convergent-divergent nozzle, also known as the de Laval nozzle. Its entire job is to take all that chaotic, swirling thermal energy generated in the combustion chamber and seamlessly convert it into directional kinetic energy. By perfectly shaping the pathway of the expanding gases, it massively accelerates the exhaust, maximizes thrust, and vastly improves the engine's overall efficiency. Section 4. Powering the final frontier, classifications and the future. Depending on the mission, engineers basically use three broad categories of propulsion. First, we've got chemical propulsion. This relies on the fuel and oxidizer reactions we were just talking about. It's the brute force required to get heavy launch vehicles off the ground, which makes it the most widely used technology today. Next up is electric propulsion. This produces thrust by accelerating electrically charged particles, like in ion thrusters. This gives you incredibly high efficiency but very low thrust, so it's absolutely perfect for those elegant, long-duration deep space missions. And finally, nuclear propulsion, which uses nuclear energy to heat a propellant. While it's still largely experimental right now, this really represents the future for deep space exploration and human missions to Mars.
So why does understanding all of this matter? Well, it matters because rocket propulsion is the absolute bedrock of modern space transportation. Literally, without these engines, we couldn't launch communication or navigation satellites into orbit, we wouldn't have human spaceflight, space station resupply missions, or really any ability to conduct vital scientific research in space. From national defense systems to deploying interplanetary spacecraft to explore the moon and beyond, propulsion is the enabling technology behind the whole shebang. Which brings us to our final thought. We've mastered chemical rockets enough to reliably access Earth orbit and send probes zipping through the solar system. But continuous advancements in propulsion technology are constantly improving our launch efficiency and drastically reducing mission costs. So I'll leave you with this question. As we perfect high-efficiency electric thrusters and finally unlock the immense power of experimental nuclear propulsion, where will these advancements take humanity next? The universe is waiting. Thank you so much for joining me for this explainer, and I'll catch you next time.